All right, let's talk about pseudo first order reactions. So, when you have a reaction in which there are two reactants, there is a technique that you can use, a little trick, if you will, to find out the order of a reaction in the traditional manner that I've shown you in lecture 3. The way you make this happen is you select the concentrations of your reactants to be vastly different from each other. Specifically, you make the concentration of A, for instance, be very small in comparison to the concentration of B. And so what happens is that as A and B react together to give you C, some amount of B does react, changing the concentration ever so slightly. But in the example that I'm pertaining right here, yes, the concentration of A changes considerably, going from left to right, but the concentration of B only changed a little bit. And if you basically use a solvent as your second reactant, the concentration of that solvent is not going to be changed all that much. And so what this basically does for you is it creates a pseudo first order reaction, because really the only thing that's going to change considerably in concentration from reactant to product is going to be just the concentration of A. An example that I can give you of this is the reaction of phenolphthalein indicator. Is the indicator used for titrations, acid-base titrations, to know when you reach the equivalence point. And if you use 0.005 molar concentration of this indicator, and you reacted with pretty much 100 times more, maybe 50 to 100 times more concentration of sodium hydroxide, which is the second reactant, then you've basically created a pseudo first order reaction condition, because the concentration of hydroxide will change as the phenolphthalein reacts with hydroxide, but it's going to change to a very small amount, a very small degree, because the concentration of phenolphthalein is very small to begin with. So the concentration of hydroxide can be regarded as being constant in the reaction. And so what you could do is look at the concentration of phenolphthalein exclusively as a function of time. So you could use a UVB spectrometer, concentrate on the absorbance of phenolphthalein, and as long as you know the absorptivity constant, you can convert the absorbance of phenolphthalein into concentration of phenolphthalein. So that's what has happened right here. And you could actually do this with a concentration of sodium hydroxide of, let's say, 0.610 molar. But you could do the same thing again, starting with 0.005 molar phenolphthalein with a concentration that is 0.305 molar. And you'll get another set of data for the reaction, right? So then what happens is you take the concentration versus time data and you start making plots. You make plot of concentration versus time, natural log of concentration versus time, and inverse concentration versus time. So if you do concentration versus time, what you're gonna basically get is a plot that in this particular case doesn't look particularly linear. And you look at the correlation values, and those values are way below 0.99, meaning that this is not going to be linear whatsoever. And you can kind of see that just by looking at the plotted points. So then you move on to taking natural log of the concentrations for runs 1 and run 2. And if you plot the natural log of the concentration versus time, in this particular example, you see that there is now a very linear correlation, right? One of them is like exactly linear. The other one is like very, very, very close to being perfectly linear. So it looks like the natural log of the concentration versus time is in fact the relationship associated with this reaction, telling you that in respect to phenolphthalein, the order ought to be first order, simply because the ln of concentration versus time yielding a linear plot implies that the reaction has to be first order from the point of view of this reactant. The other thing too is that now you get rate constants, but these are not the true rate constants. These rate constants for each one of these lines are what we call pseudo rate constants, because the value that you're obtaining from the slope of these lines is actually a combination of the true rate constant multiplied by the concentration of hydroxide raised to some power. We don't know what the order of hydroxide is in the reactions yet, But we know that the concentration of hydroxide raised to its order is going to yield this pseudo rate constant value. And the fact that the two values are different from each other means that the order of hydroxide is not zero. To figure out what that is, what we're going to do is account for the fact that the pseudo rate constant is actually the multiplication or the multiple of the true rate constant times the hydroxide concentration raised to some power. And to find out what the value of this power is, all you do is you take your two values for the pseudo rate constants, which have to equal the true rate constant times the concentration of hydroxide raised to the power of x. And for runs 1 and 2, we actually know the concentration of hydroxide, 0.610 for the first run and 0.305 molar for the second run. So you could input those values right here, and technically speaking, all you need to do is take the ratios of each. Take the ratio of the pseudo rate constants. That would have to equal the ratio of the hydroxide concentrations raised to the power of x. And of course, since we're taking the ratios, the values of k are going to cancel out. So if you plug in the ratios into your calculator for this particular example, you'll find out that you end up getting 2 equaling 2 to the x. And here you could take the logs to find out what x is, but I think it's very clear just by looking at the numbers that the value of x has to be equal to 1. And so by getting the pseudo rate constants and using the pseudo first order reaction, we have a very nifty way of figuring out the orders of both reactants. And ultimately, we use this information to also get the true value of the rate constant. What you will have to do now is simply go back to this equation up here, for which you have the value of K prime, the pseudo rate constant, plug in the value of the concentration of hydroxide, the value of X, which is found out to be equal to 1, and simply solve for regular K. All right, so that's the pseudo first order reaction. In the next video, I'm going to talk to you about mechanisms, specifically how you use what elementary steps are and how you use them to get to the rate law of the reaction.